So the first part, we're going to find our givens and our unknowns. So a golf ball rolls up a hill to a miniature golf hole. Assume the direction toward the hole is positive. So first, I'm going to go ahead and draw your small hill and the golf ball. As it says, when the golf ball is going uphill, the direction would be considered to be positive. So if it's going downhill like this would be the negative direction then. So with all word problems, you have to look for key elements or words that tells you what variables you have. So let's start with part A. If the golf ball starts with a speed of 2.9 meters per second, okay, there's some key words in that sentence that I just read. First one is starts, second one is speed, and the other one is 2.9 meters per second. Okay, looking at it carefully word by word, meters per second is the unit for velocity. I'm given the speed, which is a magnitude of velocity, and I have the word starts, right? All three terms is actually referring to initial velocity of 2.9 meters per second. So I'm going to go ahead and highlight all of this. This is trying to imply that this is my initial velocity. And notice that it starts going up a hill. So that means that the sign for my velocity is going to be positive. So I'm going to put up here, initial velocity is going to be a positive 2.9 meters per second. Let's go to the next part. And slows at a constant rate of 0.5 meters per second square. I'm going to go ahead and underline slows, constant rate, and 0.5 meters per second squared. The most important term here is actually 0.5 meters per second squared. The reason is because there's only one variable that has the units meters per second squared, and that variable is acceleration. So we now know I'm given the acceleration then. But acceleration is a vector, so I need to know the direction, or at least the sign for it. So what word tells me what sign will acceleration be then? Well, the key word is actually slows. So if the ball is going in a positive direction and is slowing down, that means the sign or its acceleration sign has to be opposite of this direction that it's going in. So if the ball is going toward a positive direction and slowing down, its sign or the acceleration sign must be negative then automatically. And so I'm going to go ahead and put the magnitude as 0.5 meters per second square. Please don't get confused with the velocity units. And let's go ahead and just highlight all of this. This is right here, all referring to acceleration then. Let's go to the last part. What is its velocity after 2 seconds? Notice we're given time because the unit for time is here, seconds. Okay. So let's go ahead and put time. I'm going to put a little subscript A to refer to part A. So I'm going to put 2 seconds. But notice there's another key word here, or two more keywords. Velocity after. So we know we're given a velocity, or we need to find velocity, and since they have the word after 2 seconds, this is actually referring to final velocity then. So my unknown is final velocity, and because this is for part A, we're going to use a little subscript A right here, and equals to question mark. Okay, part B. What is the golf ball's velocity if the constant acceleration continues for 6 seconds? Reading this carefully, we're given time because we have 6 seconds. Another key word here, velocity. And another one is constant acceleration continues. All right. So I'm going to go ahead and put what I'm given. I'm given time. I'm going to put a little subscript b, and it's going to be 6 seconds. And the wording for this is similar to the wording in part A. I'm looking for velocity if the constant acceleration continues. So that means I'm going to still use this acceleration. So I'm going to put final velocity for B equal to unknown then. And part C is more asking for a conceptual answer. So there's no math involved with this. So we're going to do the math for part A, B, and then we'll answer C once we have all our numeric values then. So I went ahead and removed the problem so that we could focus on the next step. Which kinematic equation you will use to solve this? Well, to do that, you have to look at all your givens and all your unknowns. So first look at the first given, initial velocity. Well, all four equations have initial velocity somewhere in there. So I haven't eliminated which equation yet. But if I go to the second variable, acceleration, I need acceleration to appear. Well, in the first equation, acceleration does not show up. But the second equation, acceleration shows up here, acceleration's here, and acceleration's here. So that means that I can't use this first equation right here, so I'm going to go ahead and cross it out. The third variable I have is time. I need time to be in the equation. Well, time appears here, here, but does not appear in this equation. So I'll go ahead and eliminate the fourth equation. Finally, I need final velocity then. Well, let's check. Final velocity appears here, but does not appear this third equation, so I'll go ahead and eliminate this. And it turns out that in order for me to solve this problem, I'm going to have to use this equation right here. Now we'll go ahead and plan. So we now know the equation I need is final velocity is equal to initial velocity plus acceleration times time. Alright, so let's go ahead and rearrange the equation so that it makes our math a little bit easier. And at this point, it looks like the variable that we need, final velocity, is already isolated and by itself already. So that means I won't have to rearrange the equation then. I could go to the next step. So let's go ahead and solve for part A. Part A asks for the final velocity. So put final velocity, part A, is equal to initial velocity plus the acceleration times time for part A. So plugging in our numbers that we have, remember we have our initial velocity is 2.9. We have acceleration is going to be a negative 0.5. And we have time, which is going to be 2. Let's go ahead and multiply negative 0.5 times 2, 2.9, plus 0.5 times 2, that should give you a negative 1. Alright, now remember you have a plus and a negative, so you have a 2.9 plus a negative number, or in other words, a minus 1. And 2.9 minus 1, that will be giving you 1.9. Alright, so our final velocity for part A is 1.9. Remember the units for velocity are meters per second. Okay, part B now. Part B is asking you to do the same thing. You're finding the final velocity except when time is at 6 seconds then. So we're going to use the same equation. Final velocity for part B is equal to initial velocity plus the acceleration times time for B. We'll go ahead and plug in what we know. We know for the initial velocity is 2.9. We know the acceleration is negative 0.5. And we know the time is going to be 6. So let's go ahead and solve for it. We're going to have 2.9 come down again. We're going to have my plus. You have a negative 0.5 times 6. So what's half of 6? Negative 3. Alright. So now we have 2.9. We'll go ahead and rewrite this. 2.9 plus a negative 3. That's saying 2.9 minus 3. And 2.9 minus 3, do the math, you're going to get negative 0.1. So final velocity for part B is negative 0.1, and the units for velocity again are meters per second. So now we can move on to part C. So we have two motion diagrams. The top motion diagram refers to the ball moving up the hill, and the bottom one refers to the ball moving down the hill. Remember, motion diagram is like taking several snapshots of the ball's location every second and combine them all together. So to assist you, I went ahead and calculated the ball's velocity for each second here, using the same kinematic equation that we've been using to solve part A and B. And notice that part A and part B are right here and right here. With the exception of 5.8 seconds, I just want to put this in here to show you how to draw the velocity of the ball when the velocity is going to be 0 meters per second. So and just in case you're wondering where we got these values from, okay, remember this is the time, and we plug in the time into here, and then plug into this equation, calculate it, and then whatever velocity we have, it ends up being in this column right here. Alright, so looking at the table, at t equals 0 seconds, this represents the ball's initial velocity, and it's a positive 2.9 meters per second. So I'm going to let this be time equals 0 seconds. And since this has the largest magnitude, it should have the longest vector on this diagram. So I'm going to go ahead and draw my vector. There we go. And then the next one, at time equals 1 second, the velocity decreases to 2.4 meters per second. So this is going to be my 1 second. I'm going to go ahead and draw my arrow right here. At t equals 2 seconds, the velocity is 1.9 meters per second. So this is my 2 second mark. Let me go ahead and draw the next arrow, shorter. At t equals 3 seconds, velocity is 1.4. Let's calculate. Let's go ahead and put this here. I'm going to go ahead and fill out the rest. At 4 seconds, the velocity is now 0.9, so it's getting a little bit smaller and smaller. At 5 seconds, which is going to be here, the velocity is 0.4, so it's going to be barely there. And finally, at 5.8 seconds, the velocity of the ball is going to be 0. So since the velocity is 0, we don't draw a vector for it. And then continuing down here, I'm going to let this be 5.8 seconds. And since it's 0 velocity, it's going to be represented by a little dot. And finally, at 6 seconds, which is the last drawing over here, the velocity is now negative. So it means that the direction it should be pointing to is toward the left. And notice its magnitude is 0.1. So it should be a really, really tiny arrow. So let's go ahead and draw that right there. And this is basically the motion diagram for the ball going uphill and downhill.